There was a time when the Earth had no forests, no mountains, and no familiar horizon. More than 3 billion years ago, our planet was almost entirely covered by a single vast ocean. There were no continents as we know them today, no beaches, and no coastlines stretching into the distance. Wherever you looked, there was only water beneath a sky no modern human would recognize. Most people have heard of the asteroid that ended the age of the dinosaurs. The tsunami it produced has been described as one of the most powerful wave events in Earth's history. It was not the largest wave this planet ever created. The event we're following tonight was triggered by something between 50 and 200 times more massive. Near the point of impact, the surface of the open ocean did something that should seem impossible. It boiled. Not beside a volcano, not inside a shallow lagoon. The open sea itself erupted into steam. Then the sky went dark, not over one continent, not over one hemisphere. The darkness spread across the entire planet, shutting down photosynthesis everywhere the ancient ocean reached. Every organism depending on sunlight suddenly faced the same impossible silence at the same moment, and the object responsible for all of it left behind no crater anyone can visit today. Instead, it scattered clues through some of the oldest rocks on Earth, waiting billions of years for someone to piece the story back together. Now, let's travel back more than 3 billion years to a world where the greatest wave in Earth's history began with a collision almost beyond imagination. 3.26 billion years ago, Earth occupied a chapter so distant that nearly every familiar feature of the modern world still belonged to an unimaginable future. The planet had already existed for around 1.3 billion years, carrying the marks of relentless change since its fiery beginning, yet it remained a place that would feel almost impossible to recognize. The landscapes that now shape continents, mountain ranges, and winding coastlines had not yet taken lasting form. A traveler standing there would have found almost nothing that connected this world to the one outside a bedroom window tonight. Above the ocean, the young sun shone with only about 80% of the brightness it provides today. By modern expectations, that weaker light should have left the planet much colder. Earth followed a different path. Its atmosphere held an abundant mixture of carbon dioxide and methane, forming a dense insulating blanket that trapped heat close to the surface. Despite the dimmer sunlight, the planet remained warm enough for liquid water to stretch across nearly its entire face, creating conditions where the earliest forms of life could continue their patient existence. The air itself offered no comfort for anything familiar to modern biology. Oxygen was essentially absent from the atmosphere, leaving every breath impossible for humans, animals, or plants that would appear billions of years later. Each inhalation would have carried gases unlike those sustaining life today. Even the sky may have displayed unfamiliar colors, shaped by atmospheric chemistry, very different from the one that now scatters blue light across daylight hours. Land existed only in scattered fragments. Small patches of unstable crust rose only slightly above sea level before geological forces reshaped them once again. They were temporary islands in a nearly uninterrupted global ocean, lacking broad continents or extensive shorelines. No sweeping beaches curved around familiar bays. No cliffs overlooked crashing waves. Water dominated every horizon, broken only by isolated pieces of young crust that had not yet settled into lasting stability. That ocean carried its own distinct character. Dissolved iron filled enormous volumes of seawater, joined by abundant minerals released from Earth's active interior. In shallow regions, these dissolved metals may have given the water a greenish or rusty red appearance, unlike the blue oceans known today. Every current transported chemical ingredients through an environment where geology and chemistry remained closely intertwined, each influencing the other on a planetary scale. Within those waters lived the only known inhabitants of Earth. Single celled bacteria and archaea formed the entire living world. Nothing possessed limbs, leaves, shells, or eyes. No forests softened the horizon, no fish crossed the water, and no insects drifted through the air. Every living organism consisted of a single microscopic cell carrying out the quiet chemistry of survival, division, and growth. Among these early communities, photosynthetic bacteria occupied the brightest shallows where sunlight reached the water most effectively. They gathered near the margins of the fragile crust, drawing energy from light and slowly building organic matter that supported the limited biosphere surrounding them. Their presence formed a narrow living band between stone and sea, a delicate layer spread across a planet otherwise ruled by water, minerals, and an atmosphere unlike any later age. Within that slender margin rested nearly everything life had managed to become. Imagine reducing every living thing on an entire planet to a strip so narrow that, from the perspective of geology, it would barely register at all. That was the condition of Earth's biosphere around 3.26 billion years ago. Life had gained a foothold, yet its presence occupied only a thin boundary where shallow seawater met scattered fragments of young crust. Across the rest of the planet, enormous expanses remained biologically sparse or entirely unsuitable for the forms of life responsible for sustaining the world above them. The productive heart of this early biosphere depended on sunlight filtering into coastal water. There, photosynthetic bacteria gathered in communities that transformed light into chemical energy, creating organic material that supported the limited web of living organisms around them. Their activity represented far more than one successful way of surviving. It formed the primary source of fresh biological energy entering the entire surface environment. Every generation of growth, every microscopic cell that divided, ultimately depended upon this narrow illuminated margin remaining intact. Beyond that band, the picture changed dramatically. Dry land supported no vegetation, no microbial soils comparable to those found today, and no creatures moving across exposed rock. Wind crossed bare surfaces without carrying seeds, pollen, or insects. Rain, when it fell, nourished no roots. Every piece of crust rising above the sea remained almost entirely disconnected from the living systems that now cover continents across the modern world. The deeper ocean offered little refuge for the dominant communities near the surface. Microorganisms certainly lived in darker water, yet they followed different chemical pathways and existed in much smaller populations. Many drew energy from dissolved compounds instead of sunlight, allowing them to persist in environments where light never reached. Their existence remained largely separate from the photosynthetic bacteria flourishing in coastal shallows. They did not provide an alternate foundation capable of replacing the productive engine operating at the ocean's edge. Viewed on a planetary scale, the entire biosphere rested upon a layer astonishingly thin compared with the size of Earth itself. The productive zone occupied only the upper portion of shallow coastal water, almost like a delicate coating spread across the outer surface of an immense sphere of rock and sea. Remove that slender living film, and the biological systems driving the planet would lose their central source of energy and organic production all at once. Modern Earth contains remarkable resilience through diversity and distribution. Forests, grasslands, coral reefs, freshwater lakes, deep oceans, deserts, and polar regions each shelter countless forms of life. During the Paleoarchean era, nothing resembling that redundancy existed. There were no distant ecosystems waiting to restore damaged populations. No isolated continent preserved an untouched reserve. No complex communities occupied hidden environments, ready to reclaim the surface after disaster. This made the young biosphere extraordinarily vulnerable to planetary change. A disturbance reaching the shallow coastal margins could influence nearly every organism participating in Earth's productive cycle. Recovery depended upon survivors remaining within the same fragile habitat because no equivalent population existed elsewhere. The continuity of life, balanced upon a remarkably narrow ecological foundation, maintained across a world that had invested almost all of its biological potential into one habitat, one energy source, and one delicate ribbon where sunlight met water. Evidence of a world this old cannot be gathered from towering cliffs marked by an obvious scar. It rests inside layers of stone that appear ordinary until each grain is examined with extraordinary care. Along the eastern edge of the Kopval Craton, in the Mpumalanga province of South Africa, lies the Barberton Greenstone Belt, one of the oldest exposed rock sequences anywhere on Earth. Within these rocks, sediments laid down more than 3 billion years ago remain preserved with astonishing fidelity, carrying a record that has endured while nearly every surface feature from that distant age disappeared. The Barberton Maconjwa Mountains rise across this landscape, revealing pages from Earth's earliest history where erosion has peeled away younger layers. Walking through these outcrops is less like exploring ruins and more like moving through a library written in minerals. Every exposed surface represents another opportunity to recover a fragment of an event that unfolded long before forests, animals, or even oxygen filled the atmosphere. The record survives because these rocks escaped the relentless recycling that erased so much of the young planet's crust. Among the scientists studying this remarkable archive is geologist Nadja Drabon of Harvard University. Her research, published during 2024 in the Proceedings of the National Academy of Sciences, produced the most detailed reconstruction yet attempted for the event, known as S2. Achieving that reconstruction depended upon patient fieldwork rather than dramatic discovery. Samples were collected only centimeters apart, each piece of stone preserving a tiny interval of geological time. Differences, almost invisible to the eye, gradually assembled into a sequence detailed enough to resolve events separated by what may have been individual days in the aftermath of the impact. Nothing comparable exists at the place where the object actually struck Earth. No crater marks the landscape. No circular basin invites visitors to stand at the center of the catastrophe. Billions of years of plate movement, erosion, burial, and deformation erased every recognizable surface trace of the impact itself. The story survives only because material launched high above the planet eventually settled back into ancient seas, becoming trapped inside sediments that later hardened into rock. One of the most valuable clues appears as tiny glassy spheres known as spherules. These millimeter-sized beads form when an enormous impact vaporizes rock with such intensity that droplets of molten material are blasted into the upper atmosphere. As those droplets cool, they harden into glass before falling back across enormous portions of the planet. Each layer of spherules records the aftermath of a separate collision, preserving evidence long after the crater has vanished. The Barberton Greenstone Belt contains 8 distinct spheral layers, each representing a different catastrophic impact during roughly 400 million years of Earth's early history. Researchers identify them as S1 through S8, allowing each event to be studied within its own geological context. Their thickness reveals how extraordinary these collisions were, The worldwide spherule layer associated with the Cretaceous Paleogene extinction, the impact that ended the age of the non-avian dinosaurs, measures only a few millimeters in many locations. Several Barberton layers reach a full meter, which is about 328 feet in preserved thickness, leaving behind one of the clearest surviving records of the violent skies that once shaped the earliest Earth. Within the sequence of 8 preserved impact layers, one stands apart with unmistakable weight. Geologists know it as the S2 layer, deposited about 3.258 billion years ago. It is the thickest of the entire series, and its chemistry tells a story that ordinary geological processes cannot reproduce. Every grain contributes another line to a record written at the moment an object from space encountered the young Earth with unimaginable force. One of the strongest clues comes from a metal called iridium. On Earth's surface, iridium is extremely rare because most of it sank into the planet's core while Earth was still molten. Certain space rocks, however, contain far greater amounts. When researchers examined the S2 layer, they found iridium concentrations vastly exceeding anything expected from volcanic eruptions or the normal movement of Earth's crust. The signal pointed beyond the planet itself, suggesting that the material embedded within these sediments had arrived from the depths of the solar system. The evidence becomes even stronger through the study of chromium isotopes. Isotopes are forms of the same chemical element that contain different numbers of neutrons, leaving them with slightly different atomic characteristics. Chromium carried by extraterrestrial objects possesses isotope ratios unlike those found in ordinary terrestrial rocks. Those distinctive ratios appear within the S2 deposits, providing an unmistakable chemical fingerprint of material that originated far beyond Earth's surface. Together, the iridium abundance and chromium isotope signature leave little doubt that this layer records the aftermath of an immense cosmic collision. Scientists can move beyond identifying the impact and begin estimating the size of the object itself. The thickness of the preserved layer, the diameter of the largest glassy spherules, and the concentration of extraterrestrial elements all serve as measurable clues. Computer models and laboratory analysis allow researchers to work backward from those observations, reconstructing the dimensions required to produce such an extraordinary deposit. Each independent line of evidence converges upon nearly the same conclusion, strengthening confidence in the final estimate. The object responsible was a bolide, a large body striking a planet at hypervelocity, with speeds so great that solid rock behaves almost like liquid during the collision. Based on current reconstructions, that bolide measured between 37 kilometers, which is about 23 miles, and 58 kilometers, which is about 36 miles, across before reaching Earth's surface. Its diameter approached the combined width of 4 Mount Everests placed side by side, an image that begins to hint at a scale difficult for the human mind to picture. The impact itself would have excavated a crater between 400 kilometers, which is about 249 miles, and 1,000 kilometers, that is nearly 621 miles, across. Even the smallest estimate exceeds many familiar landscapes, while the largest rivals the dimensions of entire regions. No confirmed impact structure preserved on Earth today approaches those proportions. Geological recycling has erased the scar, though the measurements preserved within ancient sediment continue to speak with remarkable clarity. For a moment, those numbers deserve to remain on their own. A body wider than many mountain ranges, arriving from space at tremendous speed, left behind evidence still visible after more than 3 billion years. The stones of Barberton preserve the consequences with extraordinary patience, revealing that the cause of this story began with an object unlike anything Earth has encountered in its later history. Perspective changes everything. A single comparison can take an event that already seems enormous and reveal that it belonged to an even greater story all along. For generations, one impact has stood as the defining symbol of planetary catastrophe, the collision that marked the end of the non-avian dinosaurs about 66 million years ago. It transformed ecosystems across the globe and reshaped the course of evolution. For understandable reasons, it became the benchmark against which every other impact has been measured. The object responsible for that famous event is estimated to have measured between 10 kilometers, which is about 6.2 miles, and 15 kilometers, which is about 9.3 miles, across. Even at that size, it released energy beyond anything humanity has experienced, excavated an immense crater, and launched tsunamis across ancient seas. Its consequences became woven into books, museums, documentaries, and classrooms around the world, establishing an image of the ultimate prehistoric disaster. The evidence preserved in the Barberton Greenstone Belt asks that familiar picture to become much larger. Calculations based upon the S2 layer indicate an incoming body between 37 kilometers, which is about 23 miles, and 58 kilometers, which is about 36 miles, in diameter. The increase appears modest when viewed only as width, yet mass grows far more rapidly than diameter. A larger sphere contains dramatically more material and therefore carries dramatically more energy when traveling at comparable speeds. By mass, the S2 impactor was likely between 50 and 200 times larger than the object associated with the extinction of the non-avian dinosaurs. That difference reaches beyond ordinary comparison. It represents an entirely different category of planetary collision, one capable of producing consequences unlike anything preserved from Earth's later history. The familiar benchmark remains extraordinary, though it no longer occupies the highest place on the scale. This realization also reshapes the story of Earth's greatest wave. Popular imagination often returns to the tsunami generated during the Cretaceous Paleogene extinction, a surge that crossed ancient oceans with devastating force. It deserves its place among the most powerful marine disturbances ever studied. Even so, the geological record from Barberton points toward an event operating on a far greater scale. The most powerful megatsunami in Earth's history struck more than 3.26 billion years ago. Almost no one alive today has heard its story, largely because the world it transformed no longer exists in recognizable form. No surviving coastline preserves its mark. No crater rises from the landscape to announce where it began. Its memory endured only through layers of sediment that escaped destruction across immense stretches of geological time. That conclusion changes more than a ranking of ancient disasters. It changes the framework through which the earliest Earth is understood. During the Paleoarchean era, impacts of astonishing size still shaped the young planet in ways almost impossible to witness directly today. Their traces remained scattered through resilient stone, waiting until modern science assembled each fragment into a coherent narrative. The scale now established invites a different way of imagining the collision itself. Numbers alone reach a limit where they stop feeling real. Beyond that threshold, only the physics of the event can reveal what such an immense body actually did during the first moments after it met the surface of the Earth. Time almost loses its meaning during an impact of this scale. The first moments unfold so rapidly that ordinary experience offers no comparison. From the instant the bolide reaches Earth's atmosphere until the surface begins to transform, only a few heartbeats pass. Within roughly 3 seconds, processes that normally require millions of years are compressed into a span shorter than a single breath. The incoming body travels at hypervelocity, meaning speeds between 20 kilometers per second, which is about 12.4 miles per second, and 70 kilometers per second, which is about 43.5 miles per second. At those extraordinary velocities, the impactor no longer behaves like a familiar solid object. The enormous transfer of energy becomes almost instantaneous. Pressures climb so high that both the incoming rock and the crust beneath it begin to flow like liquids, despite remaining composed of stone. The distinction between solid and fluid briefly disappears under conditions found only during the most violent planetary collisions. Contact begins at a single point, although that point exists for only an instant. Temperatures and pressures rise beyond the limits of ordinary geology so quickly that the surface vaporizes before the main mass of the impactor has even completed its downward motion. The explosion begins while much of the object is still arriving. Rock changes directly into vapor, producing an expanding cloud of incandescent material that races outward in every direction. At the center of the collision, a fireball grows with astonishing speed. For a brief interval, its temperature exceeds that of the sun's visible surface, creating an environment where familiar minerals cannot remain intact. Molecules separate, crystals disappear, and the distinction between rock, gas, and plasma becomes difficult to define. The landscape is rewritten through pure energy before gravity begins restoring any sense of order. At nearly the same time, the surface collapses into a temporary cavity hundreds of kilometers wide. The depression forms within seconds rather than minutes, expanding faster than any natural valley or basin could ever develop through ordinary geological change. Its walls remain unstable from the instant they appear. Gravity immediately pulls them inward again, beginning the process of collapse even before the cavity reaches its greatest dimensions. The crater exists as a rapidly changing structure instead of a fixed hole carved into the ground. The collision also sends tremendous energy through the body of the planet. Scientists estimate that an impact of this magnitude could have generated a global earthquake reaching magnitude 10 or greater. Seismic waves spread through Earth's interior, disturbing crust far beyond the collision site. Fault systems, thousands of kilometers away, which is about 1,864 miles, may have responded as the planet flexed beneath the immense release of energy. Existing volcanic regions could have experienced renewed activity as stresses traveled across the young crust. Far above the surface, another journey begins. Immense quantities of vaporized rock accelerate upward with such force that part of the material reaches escape velocity, departing Earth entirely for interplanetary space. The remainder cools while descending through the atmosphere. Tiny droplets condense into glass before returning to the surface, falling across distant oceans where they become the spherules preserved inside the Barberton rocks today. Those minute spheres remain among the few surviving witnesses to the first 3 seconds of the greatest impact recorded in Earth's earliest history. Across the impact site, the ocean changed shape before it had time to respond. Water did not rise gradually or gather into a growing swell. The collision displaced an immense volume almost instantly. Part of the ocean, above the impact, flashed into steam under extraordinary heat, while the rest was hurled outward with overwhelming force. An entire column of seawater vanished from its original position within moments, leaving gravity to begin an enormous attempt at restoring balance. As surrounding water rushed toward the newly formed cavity, the surface entered a state unlike any ordinary storm or earthquake could produce. Energy spread through the ocean in expanding pulses, carrying momentum across a world where almost nothing interrupted its passage. The sea itself became part of the impact, transferring the collision far beyond the place where rock first met water. For many years, illustrations often portrayed impact tsunamis as a single towering wall crossing the ocean. The rocks preserved within the Barberton Greenstone Belt reveal a more intricate story. Their layered sediments contain repeated deposits known as graded beds. A graded bed is a sediment layer in which the largest particles settle first, while progressively finer material accumulates above them. This orderly decrease in grain size from bottom to top is the characteristic fingerprint left behind as a tsunami gradually loses energy after sweeping across the seafloor. The remarkable feature is that these graded beds do not appear only once. They occur in stacked sequences, one above another, indicating that the same stretch of shallow seafloor experienced repeated surges instead of a single passing wave. At least two separate wave trains crossed the area in succession, and geological evidence leaves open the possibility that even more followed. Each arrival disturbed freshly deposited sediment before another pulse settled across it, creating a layered record preserved for billions of years. Every wave train reflected a different stage of the impact itself. The first pulse emerged from the immediate displacement of the ocean during the collision. Another followed as the enormous temporary crater collapsed inward under its own weight, forcing additional water outward. Later, surges likely developed as displaced seawater rushed back toward the center and interacted with the changing basin. Rather than one continuous motion, the ocean responded as a sequence of immense oscillations, each carrying tremendous energy across the young planet. Numerical models examining impacts of comparable size suggest that waves generated by such a collision could have reached heights measured in thousands of meters while traveling through the open ocean. Even 1,000 meters, that is nearly 3,281 feet, exceeds the height of many familiar peaks. These estimates extend well beyond that value, producing waves taller than any mountain range standing on Earth today. Their scale belongs to a category almost beyond ordinary imagination, where the distinction between sea and landscape briefly becomes difficult to recognize. Although no observer remained to witness those waters, the sediments remember every passage. Each layer records the gradual settling of particles after another surge swept overhead, preserving motion within stone. Long after the ocean itself transformed beyond recognition, those stacked deposits endured inside the Barberton rocks, allowing scientists to reconstruct an event whose waves crossed an almost uninterrupted global sea and left behind one of the clearest geological signatures of the greatest megatsunami in Earth's known history. Every ocean wave is shaped as much by the world it crosses as by the force that created it. On modern Earth, even the largest tsunami begins surrendering energy long before it reaches distant shores. Continental margins interrupt its path, island chains scatter its momentum, underwater ridges redirect its flow, and broad coastlines absorb part of its power. Geography continuously reshapes the wave, reducing its strength through countless interactions with the planet's varied surface. 3.26 billion years ago, those obstacles barely existed. Earth's young crust had not yet assembled into recognizable continents stretching across thousands of kilometers, which is about 1,864 miles. Only scattered fragments of proto-continental crust projected above sea level, separated by immense reaches of open water. These isolated land masses stood low against the sea and occupied only a small fraction of the planet's surface. Between them extended uninterrupted ocean, allowing motion to continue across extraordinary distances with very little interference. Under those conditions, the S2 Megatsunami encountered almost nothing capable of weakening its advance. Instead of breaking against extensive coastlines or dispersing through complicated ocean basins, the wave propagated across what was effectively a global sea. Every pulse generated by the impact retained far more of its original energy than an equivalent wave would preserve today. The young planet offered almost no barriers capable of fragmenting or redirecting such an immense disturbance. This conclusion comes from more than theoretical modeling. The Barberton rocks preserve physical evidence, demonstrating that water carried enormous quantities of sediment far beyond where those materials originally formed. Layers deposited after the impact contain mixtures of particles transported across environments that ordinarily remain separated. Their arrangement cannot be explained through ordinary tides, storms, or gradual marine currents. Only water moving with exceptional speed and tremendous volume could gather, transport, and redistribute material on such a scale. The patterns within those sediments reveal journeys extending well beyond local shorelines. Fine particles settled beside coarse fragments that originated in entirely different settings. Deposits appeared where ordinary geological processes could never have assembled them together. Each layer records another stage in the passage of immense water masses crossing an almost unobstructed ocean, carrying fragments of the seafloor with them before allowing those materials to settle once more. Among the most revealing discoveries is the presence of deep marine material preserved inside sediments formed within shallow coastal environments. Minerals and particles that should have remained far below the reach of sunlight became incorporated into deposits much closer to the surface. Their presence indicates that the megatsunami accomplished more than sweeping horizontally across the ocean. It also reached downward into deeper layers of the seafloor and water column, excavating material that ordinary waves never disturb. This vertical movement is one of the event's most extraordinary characteristics. The collision generated enough energy for the ocean to behave almost like a gigantic mixing vessel, drawing deep sediments upward while redistributing them across broad regions of the young planet. Geological boundaries separating environments became briefly erased as water connected places normally isolated from one another. Billions of years later, those transported grains remain exactly where the sea left them. Their position inside the Barberton sequence provides enduring testimony that the S2 megatsunami crossed an Earth with almost no geographical resistance. The wave did more than travel outward across the surface. It reached into the depths themselves, rearranging parts of the ocean that had remained undisturbed for immense spans of geological time. Long after the water settled, the ocean floor retained a memory that could not be erased. It remained hidden inside layers of stone until erosion gradually exposed them again, allowing geologists to examine details preserved across more than 3 billion years. Those rocks contain no written account, yet their structure records a sequence of events with remarkable clarity, revealing that the passage of the megatsunami altered far more than the surface of the sea. Ordinarily, marine sediments accumulate in orderly layers. Fine particles settle gently through the water column, forming thin laminations that remain largely undisturbed unless later geological processes reshape them. Within the deposits associated with the S2 event, that orderly arrangement disappears. The rock preserves churned sediment sequences where once distinct layers became folded, mixed, and broken apart. The original pattern of deposition survives only in scattered fragments, interrupted by forces far beyond those produced by ordinary currents or seasonal storms. Another clue appears in the form of coarse debris resting inside beds composed almost entirely of much finer material. Pebble sized fragments occur where only tiny grains should exist, embedded without the gradual sorting expected under normal marine conditions. Their presence shows that tremendous energy lifted large pieces of sediment from one location and carried them into environments where they did not belong. The ocean briefly abandoned its usual methodical rhythm and became capable of transporting material of dramatically different sizes together. The lamination within these deposits also bears the marks of intense disruption. Thin layers that once accumulated one upon another in orderly succession became twisted, truncated, and displaced. Some terminate abruptly against chaotic sediment, while others bend into irregular forms before disappearing altogether. These structures preserve the physical imprint of repeated disturbance, showing that the sea floor itself experienced deformation as enormous volumes of water passed overhead. The wave did not merely travel across the ocean floor, it penetrated into it. Powerful currents dug downward, tore loose unconsolidated sediment, and carried that material horizontally across distances impossible for ordinary marine circulation to achieve. The boundary between seabed and seawater became temporarily blurred as immense turbulence mixed particles from different depths into a single moving mass. Entire sections of the upper seafloor were excavated, redistributed, and deposited elsewhere before the ocean gradually regained stability. Evidence preserved in Barberton indicates that this process occurred repeatedly. Each arriving wave train encountered a seafloor already disturbed by the one before it. Fresh deposits laid down after the initial surge became reworked as another pulse crossed the same region, followed by yet another. Instead of one episode of disruption, the sediments record successive intervals of excavation, transport, and redeposition. Every new surge deepened the geological signature left behind. At first glance, this destruction appears to represent only another consequence of extraordinary violence. Entire layers vanished from their original positions, while others became mixed into chaotic combinations that endured for billions of years. Yet the very act of tearing open the seafloor accomplished something whose significance would emerge only after the waves had passed. Materials that had remained isolated within deeper parts of the ocean were drawn upward and dispersed into environments they had never previously reached. The rocks preserve the mechanical evidence without explaining its biological consequences. They record the excavation, the transport, and the repeated reshaping of the seabed with exceptional fidelity. Hidden within that upheaval lay the beginning of another transformation, one carried not by the force of moving water alone, but by substances released from the depths into an entirely different part of the young ocean. Water is often imagined as a shield against heat. It absorbs energy, moderates temperature, and protects life from sudden change. During the S2 impact, that familiar property reached its limit almost instantly. At the point where the bolide encountered the young ocean, the released energy overwhelmed every capacity of seawater to remain liquid. Alongside the expanding tsunami, another catastrophe unfolded at exactly the same moment, driven not by moving water, but by overwhelming heat. The collision released an amount of energy so immense that the upper portion of the ocean surrounding the impact site changed state almost immediately. This was far beyond ordinary boiling in a pot or even the vigorous bubbling produced near submarine volcanic vents. The thermal pulse forced liquid seawater to convert directly into enormous volumes of steam within moments. A substantial part of the surface ocean ceased to exist as water at all, becoming an expanding cloud of vapor racing upward into the atmosphere. The distinction is important because evaporation and flash vaporization are fundamentally different processes. Evaporation occurs gradually as individual molecules escape from a liquid surface over time. Flash vaporization happens when such tremendous energy enters the liquid so rapidly that the transition to steam occurs almost instantaneously throughout the affected volume. During those first moments after impact, the ocean did not warm step by step. It crossed the boundary between liquid and gas almost at once across the region nearest the collision. This thermal transformation unfolded independently of the giant waves already spreading away from the impact. While the tsunami carried mechanical energy through the surrounding ocean, the impact site itself became dominated by extraordinary temperatures capable of reshaping both water and rock. Steam expanded violently into the atmosphere, carrying dissolved minerals, fragments of molten crust, and countless particles generated by the collision. The sea and the sky became linked through a rapidly growing column of vapor, unlike anything produced during ordinary geological activity. The famous impact that marked the Cretaceous Paleogene extinction also generated extraordinary heat after striking a shallow coastal sea. Its effects included widespread fires, vaporized rock, and devastating environmental change. Even so, scientists have not documented evidence indicating open ocean surface boiling on the immense scale inferred for the S2 event. The difference reflects the extraordinary size of the earlier impactor and the vastly greater amount of energy it delivered to Earth's surface. Support for this conclusion comes from the Barberton rocks themselves. Their geochemical composition preserves evidence consistent with extreme thermal disruption affecting the nearby water column. Minerals record conditions that cannot be explained through ordinary sedimentation or volcanic activity alone. Instead, they point toward an episode during which seawater, dissolved chemicals, and vaporized material interacted under temperatures reached only during an impact of exceptional magnitude. For any organism living close to the collision, the advancing tsunami represented only part of the unfolding disaster. Heat had already transformed the surrounding sea before the largest waves completed their outward journey. The surface environment nearest the impact became a place where liquid water disappeared into steam, while molten material and superheated gases expanded above it. Across the young ocean, these two consequences advanced together. One traveled outward as immense pulses of moving water. The other remained centered upon the impact site, where the sea itself entered a brief state unlike any preserved elsewhere in Earth's history. The waves were already crossing the planet, and the ocean at their birthplace had already begun to boil. Long after the first waves had begun their passage, and the nearest ocean had already been transformed by overwhelming heat, another consequence continued rising above the planet. Every passing moment carried more shattered crust, vaporized rock, and superheated debris into the highest reaches of the atmosphere. The impact had become more than a local event. Earth itself was wrapping the evidence around its entire sky. The quantity of material launched upward is measured in trillions of tons. Rock that had rested within the crust only moments before now existed as microscopic fragments, molten droplets, condensed mineral vapor, sulfur compounds released from impacted rocks, and fine carbon particles produced by intense heating. Much of this material climbed high enough to escape ordinary weather. Winds in the upper atmosphere carried it far beyond the impact site, distributing it across the globe within days until nearly every horizon shared the same burden. Nothing in recorded volcanic history offers a true comparison. Even the greatest supervolcano eruptions, known from much later ages, released far less material into the atmosphere than scientists estimate for the S2 impact. Volcanoes build their eruptions through pressure accumulating beneath Earth's surface. This collision delivered its energy almost instantly, accelerating enormous quantities of crust and ocean into the sky with extraordinary speed. The resulting atmospheric load exceeded the products of any eruption preserved in the geological record. As the suspended particles multiplied, sunlight encountered an increasingly impenetrable barrier before reaching the ocean below. At first, brightness weakened. Soon afterward, ordinary daylight could no longer penetrate the thickening veil. From the surface of the sea, the sun did not appear as a dim disk struggling through haze. It disappeared completely behind a planet-wide curtain of dust, vapor, and fine mineral particles suspended high overhead. The consequences reached every corner of the young biosphere. There were no cities glowing through the darkness, no fires maintained by intelligent hands, and almost no land capable of storing warmth gathered during previous days. The scattered rocky islands rising above sea level were too limited to influence global temperatures in any meaningful way. Nearly all life depended upon shallow coastal waters that had already been disturbed by the passing tsunami and the immense transfer of heat near the impact region. Without direct sunlight, the organisms responsible for capturing solar energy could no longer continue their ordinary work. The productive surface waters that had sustained Earth's earliest ecosystems entered an unfamiliar interval in which incoming light was almost entirely absent. Every hour beneath the darkened sky reduced the energy available to support the fragile web of life already confined to that narrow marine habitat. Above those waters, fine particles remained suspended instead of falling immediately back to the surface. Their small size allowed them to circle the planet repeatedly before gravity gradually reclaimed them. The atmosphere became a global reservoir of dust, sulfur-rich compounds, condensed rock vapor, and carbon particles, extending the period of darkness far beyond the first day after impact. This was the third great catastrophe born from the same collision. The waves had crossed the ocean. Steam had transformed the waters nearest the impact. Now the sky itself had become an obstacle between Earth and its star, placing the entire biosphere beneath a ceiling through which daylight could no longer pass, leaving the future of life balanced upon whatever endurance still remained. Every living system depends upon a source of energy. On the Paleoarchean Earth, that source arrived each day as sunlight spreading across the surface of shallow coastal seas. The earliest phototrophic bacteria had evolved a remarkable ability. They captured light and transformed it into chemical energy, using that stored energy to grow, divide, repair themselves, and build the organic matter that sustained the surrounding community of life. Their existence rested upon a process so familiar today that its fragility is easy to overlook. Photosynthesis, in its simplest form, allowed these microorganisms to convert sunlight into chemical energy that could be stored within their cells. Each beam reaching the water's surface became part of an immense biological exchange, supporting countless microscopic lives across the narrow marine environments where Earth's productive biosphere existed. No forests covered distant continents, no grasslands absorbed daylight, no alternative ecosystems waited beyond the shoreline. Nearly every productive organism shared the same dependence upon light penetrating the upper layers of the sea. The darkened atmosphere interrupted that exchange everywhere at once. As dust, condensed rock vapor, sulfur compounds, and carbon particles spread around the planet, sunlight ceased to reach the waters where these microorganisms lived. Their supply of usable energy did not gradually weaken through changing seasons or shifting climates. It stopped. Across oceans separated by enormous distances, the interruption unfolded almost simultaneously beneath the same opaque sky. Unlike many organisms that would evolve much later, these early phototrophic bacteria possessed no reserve strategy capable of replacing sunlight on a planetary scale. They could not migrate toward brighter regions because no brighter regions remained. They could not switch to another abundant energy source because none existed within their ecological role. Every passing day, beneath the darkened atmosphere, reduced the energy available for growth, reproduction, and the continual renewal upon which their populations depended. The consequences extended far beyond the microorganisms themselves. They formed the productive foundation of the shallow marine communities occupying Earth's surface. Organisms feeding directly upon them immediately encountered declining food availability. Those depending upon the consumers above them inherited the same shortage. Even within these comparatively simple ecosystems, energy flowed through connected relationships. When the first link weakened, every remaining connection experienced the loss. Nothing resembling a regional famine unfolded. The interruption reached nearly every productive habitat existing on the young planet. Earth's biological engine operated within a remarkably narrow environmental band, and that entire band had lost access to the sunlight, driving its metabolism. There was no untouched refuge where ordinary productivity continued, no distant continent preserving an independent reservoir of life, and no flourishing deep ocean ecosystem capable of replacing what had vanished near the surface. By this stage, the separate disasters born from the impact no longer acted independently. The immense waves had overturned the habitats where these microorganisms lived. Extreme heat had transformed nearby waters during the first moments after collision. Now the prolonged darkness removed the energy supporting recovery itself. Physical destruction, thermal disruption, and global light deprivation converged upon the same communities, occupying the same fragile environment. For the first time in Earth's history, nearly the entire surface biosphere faced the same crisis together. The organisms that gathered sunlight, the organisms that depended upon them, and the delicate chain linking one form of life to another all entered the same prolonged interval, sustained only by whatever energy remained within living cells before the sky had closed above them. Far below the darkened surface, another world continued according to different rules. It had never depended upon daylight crossing the sea, nor had it relied upon the narrow coastal waters where nearly all productive life gathered. The events transforming the upper ocean into a place of shattered waves, intense heat, and prolonged darkness unfolded at a distance from these deeper habitats, where energy arrived through entirely different pathways. Among the organisms living there were chemoautotrophs, microscopic forms of life that generated energy from chemical reactions instead of sunlight. They obtained that energy by oxidizing substances such as iron, sulfur, or hydrogen released from Earth's interior or produced through natural geological processes. Rather than capturing light, they transformed chemical energy into the compounds needed for growth, reproduction, and survival. Their existence was linked to the planet's internal activity instead of the daily cycle between the sun and the sea. Sharing these environments were hyperthermophiles, organisms capable of thriving at temperatures that would destroy most other forms of life. Many occupied habitats surrounding hydrothermal vents scattered across the deep seafloor. There, mineral rich fluids emerged from fractures in the crust after circulating through hot rock below. These vents created stable chemical environments where life could flourish despite complete darkness, supported by heat and dissolved compounds rising from within Earth itself. Because these communities occupied the deep ocean, they remained separated from the worst effects unfolding near the surface. The greatest violence of the tsunami swept across upper waters and shallow marine shelves. Surface boiling was concentrated around the impact region, where unimaginable energy had transformed the ocean into expanding clouds of steam. The disappearance of sunlight reached across the globe, yet these organisms had never depended upon sunlight to begin with. Their ecological foundation remained rooted in chemical reactions continuing beneath the disturbed seas. Their persistence did not arise from extraordinary resistance to catastrophe. They were not stronger than the microorganisms inhabiting the illuminated coastal waters, nor did they possess unique adaptations specifically suited to asteroid impacts. Their survival reflected geography and metabolism. They occupied environments the catastrophe could not efficiently penetrate, and they relied upon energy sources that remained available after daylight had vanished from the planet. Geological evidence suggests remarkable continuity in these deep dwelling communities before and after the S2 event. Chemical signatures associated with these forms of life do not display the dramatic interruption expected if their populations had suffered widespread collapse. Their presence remains broadly consistent across the sedimentary record, implying that the impact altered their surroundings far less severely than it transformed the productive surface waters supporting the visible biosphere. At the time, these organisms represented only a background population within Earth's broader story of life. They produced no sprawling ecosystems visible from above and occupied habitats far removed from the shallow environments where biological productivity was concentrated. Few signs of their existence appeared within the sunlit waters that had dominated earlier chapters of the planet's history. Yet their continued existence preserved an unbroken thread through the catastrophe. While the surface biosphere struggled beneath collapsing food webs, darkness, and disrupted oceans, these chemically sustained communities continued drawing energy from Earth's interior. They remained where they had always been, largely untouched by the sequence of disasters unfolding overhead, their enduring presence becoming unexpectedly important as the wounded planet entered the weeks that followed. Some stories are written with bones, shells, or footprints. This one is written with atoms. Long after every wave had settled and every cloud of debris had become part of the rock, the chemistry of carbon preserved a record no eye could have witnessed. Across the ancient layers, the balance between two naturally occurring forms of carbon became a memory of life itself, tracing moments of abundance and moments when the living world nearly lost its voice. Carbon isotope analysis allows scientists to read that memory. Carbon exists in several forms, including carbon-12 and carbon-13. Living organisms do not use these forms in exactly the same proportions. During growth, many photosynthetic microorganisms naturally favor carbon-12 over carbon-13. As they multiply, die, and become buried within sediment, they leave behind a distinct chemical pattern. Different kinds of organisms and different metabolic pathways create different balances between these two forms of carbon. Layer after layer, those changing ratios build a continuous archive of biological activity stretching across immense spans of time. In the sediments deposited before the S2 impact, that archive shows a world functioning according to familiar rhythms. The shallow Paleoarchean seas supported thriving communities of photosynthetic microorganisms. Day after day, sunlight reached the ocean's surface, allowing these tiny cells to transform light into chemical energy and build new organic matter. Their activity became woven into the sediment, leaving carbon isotope patterns that speak of steady productivity across broad regions of the ancient ocean. Then the record reaches the impact layer. The change is unmistakable. Carbon isotope signatures associated with abundant photosynthetic life decline sharply. The chemical pattern that had remained comparatively stable breaks abruptly, reflecting a dramatic collapse in biological productivity near the ocean surface. This shift does not represent the disappearance of carbon itself. Instead, it reveals that the organisms responsible for producing so much organic material had been reduced with extraordinary speed. The chemistry preserved inside the rock captures that transformation without requiring a single fossil to explain what happened. For geochemists, this signal approaches the closest equivalent to a biological death certificate. A physician may place instruments upon a patient and observe the rhythm of a heartbeat fade into a flat line. Earth's oldest oceans possessed no such instruments, yet the carbon preserved within these sediments performs a similar role across billions of years. The once active chemical signature of surface productivity weakens so dramatically that it marks the lowest point yet reached in the story recorded by these rocks. Every catastrophe described until now converges within this single chemical horizon. The impact had already shattered the ocean. The heat had transformed water into expanding steam near the collision site, and the dust filling the atmosphere had removed the sunlight, sustaining the surface biosphere. Together, they silenced the biological engine that had driven nearly all productive life across the upper ocean. The carbon isotope record does not describe crashing waves or darkened skies. It reveals their consequence with remarkable clarity. Within this thin layer of stone rests the chemical imprint of a planet where the productive surface ecosystem had fallen into its deepest collapse, leaving only the faintest trace of the thriving world that had existed immediately before. Then, without warning, the rocks changed their voice. The impact layer marks the deepest collapse yet recorded, preserving the chemical signature of a surface biosphere pushed toward failure. One might expect the sediments above it to continue that decline, documenting a long struggle back toward stability. Instead, the layers resting directly upon the impact deposit present something entirely different. Their chemistry does not speak of hesitation. It records a recovery that begins with surprising speed, unfolding far sooner than the preceding catastrophe seems to allow. Carbon isotope analysis once again provides the key. The same chemical patterns that revealed the collapse now reveal its reversal. Biological productivity markers rise sharply above the impact horizon. The signal does not creep upward across countless generations. It rebounds across a comparatively short interval, preserved within the sediments. Whatever happened after the darkness spread across the planet, life at the ocean surface did not remain trapped in prolonged decline. The rocks contain another remarkable detail. In several studied sequences, carbon-rich microbial layers deposited after the impact are packed more densely than comparable layers beneath it. These accumulations represent periods when microbial communities were producing abundant organic material, enough to leave an unusually strong imprint within the sediment itself. Such deposits suggest that certain populations did not merely return to their former abundance, they expanded beyond it, creating biological activity that exceeded what had existed before the collision reshaped the planet. This pattern has drawn careful attention from researchers studying the Barberton record. Nadja Draban and her colleagues describe the response using a single word that stands apart because of where it appears in the story. They write that life bloomed after the impact. That choice carries unusual weight. A bloom evokes rapid multiplication, widespread growth, and favorable conditions supporting extraordinary biological expansion. Encountering that description immediately after evidence for one of Earth's greatest impact disasters forces the ancient sediments into an unexpected conversation with the assumptions brought to them. The sequence now refuses to behave like a familiar extinction narrative. The waves had crossed nearly every reachable sea. Extreme heat transformed the surface waters near the collision into expanding steam. Rock vapor and dust erased sunlight from the world above. Carbon isotope signatures recorded the collapse of photosynthetic productivity. Every line of evidence pointed toward a biosphere driven to its lowest state. Yet the layers immediately following that crisis preserve a different outcome, one in which microscopic communities multiplied with remarkable vigor instead of fading into geological obscurity. Nothing in these observations diminishes the scale of the catastrophe. The devastation remains written throughout the impact bed with extraordinary clarity. Even so, the sediments insist that destruction and renewal stand side by side within the same sequence of stone. Scientists continue working to understand the mechanism connecting those two realities. The evidence leaves little doubt that the rebound occurred. Explaining why it happened remains one of the most compelling chapters preserved within the oldest surviving rocks on Earth. Somewhere during the weeks and months after the impact, conditions shifted in a way that transformed a planet emerging from disaster into one capable of supporting an unexpected biological bloom. The answer begins with an element that rarely receives attention outside the laboratory, yet every living cell depends upon it. Phosphorus does not provide energy by itself, nor does it capture sunlight. Instead, it forms part of the physical framework that allows life to exist at all. Wherever a cell grows, divides, or passes information to the next generation, phosphorus is present, woven into the machinery that makes those processes possible. Its importance reaches every level of biology. Phosphorus forms part of deoxyribonucleic acid, the molecule carrying hereditary information from one generation to the next. It also forms part of ribonucleic acid, which helps translate that information into the proteins every cell requires. Another phosphorus containing molecule, adenosine triphosphate, stores and transfers the chemical energy cells use to power nearly every activity essential for survival. Even the membranes surrounding each cell depend upon phosphorus-rich compounds to maintain their structure. Without phosphorus, cells cannot replicate, cannot preserve their internal organization, and cannot sustain the countless reactions that define life. Across the Paleoarchean world, this element remained in limited supply. The young oceans contained comparatively little freely available phosphorus, leaving microorganisms to compete for every accessible source. Biological productivity within the shallow seas was constrained not only by sunlight, but also by this persistent nutrient scarcity. Even during favorable conditions, the capacity for growth depended upon obtaining enough phosphorus to construct new cells. The available supply placed a ceiling upon how rapidly microbial communities could expand. Then the impact changed that balance with astonishing speed. According to estimates presented by Nadja Draban and her colleagues, the S2 impactor introduced approximately 360 billion metric tons of extraterrestrial phosphorus directly into Earth's oceans during the collision. This material had traveled through space, enclosed within the body of the impactor itself. When the object struck, the tremendous release of energy shattered its minerals, dispersing phosphorus across an immense region of the ocean. Geological processes that might otherwise require immense spans of time unfolded within moments. Nothing comparable had previously occurred in Earth's biological history. Rivers had not delivered this nutrient. Weathering had not released it grain by grain from continental rocks. Volcanic activity had not supplied it through repeated eruptions. A single extraterrestrial body injected an extraordinary quantity of phosphorus into the planet's interconnected oceans almost instantaneously, transforming the chemical environment with remarkable efficiency. The contrast is difficult to overlook. The same collision that launched towering waves across the seas, transformed surface water into expanding steam, and filled the atmosphere with light blocking debris, also carried within its own chemistry the raw material required for renewed biological growth. Destruction and opportunity arrived together, inseparable parts of the same event, preserved within the oldest surviving rocks on Earth. This immense nutrient delivery provides the first plausible mechanism explaining the rapid rebound recorded above the impact layer. Microorganisms that endured the catastrophe suddenly found themselves surrounded by a resource that had long restricted their expansion. The rocks suggest that this change mattered profoundly. Even so, phosphorus alone cannot account for every detail of the extraordinary bloom. Another process had begun unfolding alongside it, one equally tied to the violence of the impact and equally important in shaping the surprising recovery that followed. The clues resting above the impact layer invite another look at the ocean floor itself. Earlier, the torn sediments hinted that something more than rock had been carried upward. The scars preserved in those layers point toward a transformation that reached far beyond broken seabeds. The violent churning had opened a pathway between waters that had remained separated for immense spans of time. The deep Paleoarchean ocean differed greatly from the shallow waters where sunlight reached the surface. Oxygen remained extremely scarce throughout much of the planet, allowing enormous amounts of dissolved iron to accumulate in the colder depths. That iron stayed trapped below the illuminated surface, largely unavailable to the microbial communities living where light powered growth. For countless generations, this separation limited how much life could expand, even when sunlight remained plentiful. The giant waves unleashed by the impact did more than sweep across the sea. Their immense force tore into the ocean floor, displaced deep water, and drove powerful upwelling across broad regions. Water that had rested far below the surface was thrust upward, carrying its dissolved chemical cargo into places it had rarely, if ever, reached before. Material that normally remained isolated entered the illuminated upper ocean within an extraordinarily short span of geological time. Among the substances rising from the depths, iron proved especially important. Many early microorganisms depended upon iron within essential metabolic pathways. Certain iron metabolizing bacteria relied on it while capturing energy from sunlight or while carrying out chemical reactions that supported growth and reproduction. Even where sunlight eventually returned, productivity could increase only if vital nutrients accompanied that light. The deep ocean had contained exactly those ingredients, waiting beyond the reach of surface ecosystems until the impact rearranged the water column. This new supply arrived alongside another extraordinary contribution. The impactor itself delivered an immense pulse of phosphorus into the ocean, adding one of the rarest biological resources of the Paleoarchean world. Phosphorus formed part of deoxyribonucleic acid, the the molecule cells used to store and transfer energy, and the membranes surrounding every cell. Iron and phosphorus served different biological purposes, yet together they removed two major limits that had long restrained microbial productivity across the shallow seas. Within an interval far too brief for ordinary geological change, nutrient poor surface waters became enriched on a planetary scale. The catastrophe had mixed reservoirs that normally remained apart, while also introducing fresh material from beyond Earth itself. Conditions that had once restricted biological expansion shifted with astonishing speed. The same sequence of events that devastated the surface ocean also reorganized its chemistry into something entirely new. The rocks preserve this change without intention or exaggeration. Their chemical record suggests that the destruction did not mark the end of the story unfolding across the sea. By stirring iron upward from the depths and adding an unparalleled delivery of phosphorus from the impactor, the event created the richest nutrient environment the Paleoarchean ocean had yet experienced. The disaster had not merely spared life, it had unknowingly prepared the conditions from which an unexpected flourishing could emerge. A different pattern begins to emerge the moment the eye moves above the impact layer. The change is not first seen in the shapes of the rocks or the textures of the sediment. It appears within the chemistry itself, preserved as a subtle alteration in the balance of carbon locked inside the minerals. The signal is remarkably clear. Directly above the S2 impact bed, the ratio between carbon 12 and carbon 13 changes in a distinct step. It does not drift across long stretches of time. It shifts within a comparatively narrow interval, marking the arrival of a transformed biological world. Carbon isotope analysis allows ancient life to leave traces long after individual cells have disappeared. Different groups of organisms process carbon in slightly different ways while building their tissues. Those differences create characteristic proportions of carbon 12 and carbon 13 that become preserved within sediments after the organisms die. Layer by layer, the rocks accumulate these chemical patterns, forming a continuous record of biological activity. When that pattern changes abruptly, it signals more than ordinary environmental variation. It indicates that a different style of life has become unusually abundant. The layers immediately above the impact preserve exactly such a transition. The chemical fingerprint no longer matches an ecosystem dominated almost entirely by sunlight-powered communities. Instead, it reflects a rapid expansion of organisms following another metabolic pathway. Their growing influence altered the overall isotope balance of the shallow ocean strongly enough for that change to remain visible across billions of years. The rocks do not preserve individual cells in perfect detail, yet they preserve the collective chemistry of an ecosystem that had reorganized itself with surprising speed. The isotope evidence points most consistently toward iron metabolizing bacteria. These microorganisms relied upon chemical energy derived from iron oxidation instead of depending primarily upon sunlight reaching the ocean's surface. They had always been present within the Paleoarchean biosphere, occupying environments where iron remained plentiful and light contributed little to survival. Before the impact, however, they represented only part of a much broader microbial community. Photosynthetic organisms shaped the productive surface waters, while iron metabolizers occupied a less prominent role within the overall biological balance. Everything changed after the impact, rearranged the chemistry of the ocean. Darkness still limited photosynthetic growth, even as the surface slowly stabilized. At the same time, immense quantities of dissolved iron had been lifted from the depths, while phosphorus from the impactor enriched waters that had long been nutrient poor. Those conditions favored organisms already adapted to extracting energy from iron. Their populations expanded into an environment suddenly filled with resources that matched their metabolism with remarkable precision. The chemical record captures the result with unusual clarity. The biological hierarchy that had characterized the shallow ocean before the catastrophe no longer occupied the leading position afterward. Iron metabolizing bacteria flourished while sunlight dependent communities rebuilt themselves from severe disruption. The impact that came closest to ending life on Earth also reorganized the biological hierarchy of the entire ocean through consequences that no living organism could have anticipated. The catastrophe became an unexpected architect of a new marine world, leaving its signature written not only in broken stone, but also in the enduring chemistry of life itself. One impact layer might be dismissed as an extraordinary accident preserved by unusual fortune. The rocks of the Barberton Greenstone Belt tell a broader story. They contain not one unmistakable record of a colossal collision, but 8 separate impact layers, deposited across an interval stretching from approximately 3.6 billion years ago to about 3.2 billion years ago. Each layer marks another encounter between the young Earth and an object arriving from space with enough energy to leave a permanent signature in the geological record. Among these events, the S2 impact remains the largest supported by current evidence. Even so, it did not stand in complete isolation. The neighboring events, known as S1, S3, and S4, also represent impactors of extraordinary size, approaching S2 closely enough that each would have transformed the planet on a scale beyond any disaster witnessed during later geological history. Their repeated appearance within the same ancient sequence suggests that collisions of this magnitude belong to the ordinary rhythm of the Paleoarchean world far more than they do today. Viewed together, these layers change the meaning of the story. S2 was not a singular interruption imposed upon an otherwise stable planet. Earth existed during an era when enormous impact events returned again and again across millions of years. Oceans recovered, microbial ecosystems reorganized, and before enough time had passed for those changes to become permanent, another collision could arrive with the power to reshape the environment once more. Planet-scale disruption formed part of the background against which early life evolved. Each impact would have differed in angle, location, composition, and energy. Even so, the same broad processes likely accompanied many of them. Seawater mixed with deeper reservoirs. Sediments were disturbed across immense distances. Nutrients entered environments where they had previously been scarce. Chemical boundaries separating different parts of the ocean became temporarily erased. Organisms that had occupied minor ecological roles could suddenly encounter conditions favoring rapid expansion, while formerly dominant populations struggled to adjust to transformed surroundings. This possibility carries remarkable implications for understanding early biological diversification. If repeated impacts delivered phosphorus from extraterrestrial material, lifted dissolved iron into sunlit waters, and repeatedly reorganized microbial communities, then these catastrophes may have acted as engines of biological innovation instead of functioning only as destructive interruptions. Each event could have reshaped ecological opportunities, encouraging different metabolic strategies to expand whenever environmental conditions shifted in their favor. Evolution would have unfolded within a world repeatedly altered by forces arriving from beyond the planet itself. Even this sequence of 8 impacts may represent only a fraction of the original history. The Barberton rocks preserve an exceptionally rare archive, surviving from an age whose surface has almost entirely disappeared. Plate tectonics recycled most of Earth's earliest crust back into the planet's interior, carrying countless ancient landscapes beyond recovery. Other impact layers almost certainly vanished with them. The surviving record therefore offers a glimpse rather than a complete catalog, suggesting that the young Earth may have experienced even more frequent planetary collisions than the rocks can still reveal. The absence of an enormous crater may seem puzzling after tracing the consequences of such immense impacts through ancient rocks. If an object large enough to reshape the oceans struck Earth, it seems reasonable to expect that its scar should still dominate the landscape today. The explanation lies within the restless nature of our planet itself. Earth does not preserve its oldest surface, it continually remakes it. This transformation is driven by plate tectonics, the slow movement of Earth's crustal plates across the planet's surface. As these plates shift over immense spans of time, new crust forms along mid-ocean ridges, while older crust gradually sinks back into the mantle through subduction. Mountains rise and wear away. Ocean basins open and close. Continents collide, separate, and change shape. The ground beneath every landscape participates in a cycle of destruction and renewal that has operated for billions of years. A crater measuring somewhere between approximately 400 kilometers, which is about 249 miles, and 1,000 kilometers, that is nearly 621 miles, across might appear impossible to erase. Yet no feature can remain untouched after 3.26 billion years of geological recycling. Sections of the crater may be pulled into the mantle. Other parts may be buried beneath younger rock. Heat and pressure can distort its original form until nothing recognizable remains. Wind, water, volcanic activity, and continental deformation continue the process, removing another layer of evidence with each passing age. Eventually, the crater itself disappears, even though the impact that formed it once altered the entire planet. The Barberton impact layers survived for a very different reason. They were never enormous landforms standing above the surrounding terrain. They existed as remarkably thin sedimentary deposits that settled through ancient water before becoming buried beneath younger layers. Once enclosed within the stable rocks of the Kapval Craton, they escaped much of the intense deformation that affected other regions of Earth's early crust. Their survival depended upon rapid burial and extraordinary geological stability, allowing delicate chemical and mineral signatures to remain intact across billions of years. Looking outward reveals a striking contrast. The moon possesses no active plate tectonics to recycle its crust. It has almost no atmosphere capable of driving long-term erosion, and no oceans to reshape its surface. Ancient craters remain where they formed, overlapping one another across landscapes that have changed very little since the earliest history of the solar system. Impacts that occurred during the same era recorded in the Barberton rocks still mark the lunar surface with remarkable clarity. Seen together, these two worlds preserve complementary histories. Earth remembers through scattered chemical traces locked inside ancient sediments, while the moon remembers through enduring landscapes carved into stone. One archive is subtle, the other unmistakable. In that sense, the moon has become Earth's memory, preserving visible monuments from an age of relentless bombardment after our own planet recycled nearly every crater that once told the same story. The rocks beneath southern Africa survived only because they recorded the consequences, instead of preserving the wound itself. Some of the deepest discoveries in Earth science begin with something that is missing. In the layers surrounding the S2 impact event, researchers can trace shattered minerals, microscopic spherules, chemical disruptions, and changes in ancient biological activity with impressive confidence. Those clues combine into a remarkably complete account of an event that transformed the young planet. Yet, after following every available trail through the rocks, one expected landmark remains absent. The place where the impact occurred has never been found. There is no confirmed crater. No preserved basin marks the point where the object struck Earth's surface. No surviving landscape can be identified beyond reasonable doubt as the center of the collision. This absence may seem surprising after scientists have reconstructed so much of the event itself. The size of the impactor can be estimated, its effects on the oceans can be modeled, and its influence on early life can be measured through carefully preserved geological evidence. Even so, the location where everything began has disappeared from the surface of the planet. The chemical evidence does provide one important clue about the object itself. Tiny fragments preserved within the ancient sediment point toward a carbonaceous chondrite. This is a type of carbon-rich space rock that contains organic compounds together with minerals that formed in the presence of water. Such objects preserve material dating back to the earliest history of the solar system. Their composition makes them valuable scientific records, offering a glimpse of conditions that existed long before Earth became a stable world with oceans and continents. Even with this information, the exact birthplace of the impactor within the solar system remains uncertain. Several possible source regions exist, but no single origin can yet be demonstrated with confidence. The missing crater is unlikely to reflect a lack of careful investigation. The Earth has been reshaping its own surface for approximately 3,260,000,000 years since the S2 event. Mountains have risen and worn away. Ocean basins have opened and closed. Layers of rock have been folded, fractured, buried, and altered by heat and pressure. Plate tectonics, the slow movement of Earth's crustal plates that carries old crust downward into the mantle while fresh crust forms at mid-ocean ridges, has recycled much of the surface that existed during the Paleoarchean. Any crater measuring hundreds of kilometers across, which is about hundreds of miles across, would have faced an almost unimaginable span of geological change. Because of that relentless recycling, the impact site may no longer exist in any recognizable form. It could have been carried into the deep interior of the planet, broken apart by tectonic forces, or buried beneath younger rock beyond practical recovery. Future discoveries may refine the story, yet there is no guarantee that even more advanced technology will uncover a crater that Earth's own geology has permanently erased. That uncertainty does not weaken the scientific picture. In many ways, it highlights the strength of the evidence. Researchers have reconstructed the consequences of one of the most violent events in Earth's early history through chemistry, sedimentology, and the fossil record left by microscopic life. They can describe the aftermath with surprising precision while acknowledging that the exact point of impact remains unknown. The missing crater stands as a reminder that science can illuminate enormous chapters of the past, even when one of its most dramatic landmarks has vanished beyond recovery. The story no longer belongs to Earth alone. As researchers expanded their search beyond our own planet, another landscape began to reveal traces of an event that felt unexpectedly familiar. High above the surface of Mars, orbiting spacecraft captured detailed images of broad plains, ancient craters, and patterns carved into terrain that had remained unchanged for immense spans of time. Among those discoveries was a crater now known as Pole, identified by planetary scientists in 2019 within the northern lowlands, a region where geological evidence indicates a shallow ocean once stretched across the Martian surface. The crater measures approximately 110 kilometers across, which is about 68 miles. Around it, the surrounding landscape displays unusual deposits extending far inland from what would have been the ancient shoreline. Rather than forming random patterns, these materials appear to follow broad paths that spread away from the crater in sweeping arcs. Researchers interpret these formations as Paleotsunami run-up deposits, sediment, and debris carried inland by an enormous wave before settling across the landscape. Their orientation, distribution, and distance match what computer models predict for a megatsunami, triggered by an impact into shallow water. The estimated scale is extraordinary. Scientists calculate that the advancing wave may have reached heights approaching 250 meters, which is about 820 feet, after striking land. From the impact site, the water may have continued inland for as much as 1,500 kilometers, which is about 932 miles. Even after losing energy across the landscape, the flow retained enough force to reshape the surface over an immense area, leaving behind features that remain visible because Mars lacks the active geological recycling that continually transforms Earth. Although separated by worlds and by vast stretches of time, the physical process bears a remarkable resemblance to the S2 event recorded in Earth's oldest surviving rocks. In both cases, the impact appears to have occurred within an ocean or shallow marine environment. Neither world possessed large continental barriers capable of absorbing the full momentum of the expanding waves. Water became the primary vehicle through which the collision spread its influence, carrying energy across enormous distances while disturbing sediments, redistributing materials, and altering environments far beyond the point of impact. This comparison carries an important implication. The S2 event was not an isolated curiosity produced by unusual circumstances found only on Earth. During the early history of the inner solar system, collisions between large space rocks and young planetary surfaces were far more common than they are today. Wherever liquid water collected across broad open basins, impacts possessed the ability to unleash waves on a planetary scale. Oceans became participants in these events, transmitting their energy across horizons that extended far beyond the crater itself. Mars preserves this chapter with exceptional clarity because much of its ancient surface escaped the relentless recycling that reshaped Earth. Our own planet retained only scattered geological signatures, fragments of a story protected within rare formations that survived billions of years of change. Mars, by contrast, still carries visible reminders across its landscape. Together, these two worlds reveal that the early inner solar system was shaped by recurring violence, and wherever an ocean existed, its waters carried the consequences of those distant collisions. After following the evidence through shattered minerals, chemical signatures, ancient sediments, and the faint record left by microscopic life, a larger pattern begins to emerge. It is not an idea imposed upon the rocks. It is a pattern carried within them. Each layer contributes another fragment until the record itself presents a question that could not have been asked at the beginning of this journey. If impacts repeatedly transformed the conditions that supported life, if each collision rearranged nutrients, circulation, and biological opportunity Then what relationship existed between catastrophe and survival on the early Earth? This is not a departure from geology into speculation. The question grows directly from measurable observations. The S2 impact layer preserves evidence for widespread devastation across the surface ocean. Immediately above it, the same sequence preserves signs of renewed biological activity, changing nutrient availability, and a different balance among microbial communities. Those discoveries do not erase the destruction that came first. They show that destruction and biological change became linked through physical processes that can still be measured after billions of years. For many extinction events preserved in younger rocks, the familiar story follows a recognizable sequence. A crisis removes enormous numbers of organisms. The environment gradually stabilizes. Survivors expand into empty ecological roles until ecosystems resemble their earlier forms once again. Recovery is often described as persistence through hardship, followed by the rebuilding of what existed before the disruption. That framework has guided much of paleontology because it explains many chapters of Earth's later history with considerable success. The Paleoarchean record surrounding the S2 impact points toward a different pattern. Before the collision, the shallow ocean supported one biological arrangement. After the collision, the chemistry of the ocean changed rapidly. Nutrients became available in ways that had not existed previously, and different microbial populations expanded with unusual speed. The evidence does not suggest that the surface biosphere returned to an earlier condition without alteration. Instead, the biological hierarchy itself shifted. Some organisms declined, others that had occupied more limited roles became far more abundant as environmental conditions changed around them. Seen in this light, recovery becomes an incomplete description. The rocks indicate transformation instead. Life continued, yet it continued along a pathway shaped by the consequences of the impact. The collision altered the environment, and the altered environment favored different forms of metabolism. Evolution did not resume on an unchanged stage. The stage itself had been rebuilt by geological forces operating at a planetary scale. That possibility carries unusual weight because it emerges from evidence gathered independently through sedimentology, isotope, geochemistry, impact modeling, and the fossil record preserved within ancient microbial deposits. Together, these observations describe more than survival. They reveal interaction between planetary processes and biological history, with each influencing the other across immense spans of time. The question that remains belongs entirely to science. If repeated impacts consistently reorganized oceans, redistributed nutrients, and opened opportunities for different communities of microorganisms, then catastrophic events may have contributed to the direction of early evolution itself. The rocks do not offer a complete answer. They establish that the question is worth asking because it is written into the oldest surviving chapters of Earth's history. Life during the Paleoarchean occupied a surprisingly narrow stage. Every confirmed trace points toward the same setting: shallow coastal seas where sunlight reached the water, and the edges of the earliest continental crust provided stable places for microbial communities to grow. The living world had not yet spread across continents because no plants or animals existed to claim dry land. Neither had it established a complex refuge in the deep ocean. The entire known biosphere rested within a remarkably limited environment, gathered along a fragile ribbon where light, water, minerals, and chemistry briefly aligned. That narrow distribution carried profound consequences. There was no second ecosystem waiting elsewhere if these coastal communities vanished. No forests stood inland. No thriving plains covered the continents. No independent network of organisms occupied the deepest waters, ready to rebuild what had been lost. The biological world possessed very little redundancy. Survival depended upon one interconnected population, occupying conditions that were favorable yet vulnerable to a single disturbance large enough to reshape the entire planet. The geological record reveals that the S2 impact pushed those conditions toward their limit. Researchers have reconstructed an event capable of transforming the atmosphere, disturbing the oceans, and disrupting the very environment upon which those early phototrophic organisms depended. The evidence preserved within the rocks demonstrates that life endured. It does not suggest that survival was comfortable or guaranteed. Every surviving chemical signature points toward a biosphere compressed into an exceptionally narrow window between persistence and disappearance. A small alteration in the impact conditions could have changed that outcome. Had the object struck a slightly deeper portion of the ocean, different volumes of seawater and seafloor material might have entered the atmosphere. Had the airborne dust remained suspended for a longer interval, sunlight reaching the coastal shallows could have been reduced beyond the endurance of many phototrophic microbes. A somewhat greater thermal pulse might have expanded the zone where surface waters became temporarily uninhabitable. None of these possibilities require imagining a different planet. They represent modest changes within the range of impact physics that scientists already understand. Those possibilities matter because the remarkable influx of phosphorus and iron described in the previous chapters depended entirely upon living organisms remaining to use those resources. Nutrients possess no biological value in the absence of biology itself. An ocean filled with phosphorus and dissolved iron would not rebuild an empty biosphere. It could only nourish cells that survived long enough to divide, spread, and occupy the transformed environment. The extraordinary bloom recorded after the catastrophe therefore carries an unspoken condition. Enough life remained to seize the opportunity that the impact had unintentionally created. The rocks preserve both halves of that story. They record devastation on a planetary scale, followed by unmistakable signs of renewed biological activity. Between those chapters lies a boundary that cannot be measured directly. No mineral layer states how many cells endured or how close the biosphere came to complete collapse. Even so, the sequence preserved across the Barberton record shows that the margin was real. Recovery followed, yet it emerged from conditions that had approached the limits of what the early living world could withstand. The evidence does not describe an effortless return. It reveals a biosphere that crossed an extraordinarily narrow threshold, surviving by enough to continue Earth's story, while leaving no indication that the distance between survival and absence had ever been comfortably wide. There are moments in Earth's history when the evidence refuses to separate one story from another. The S2 impact belongs among those moments. Every layer of preserved rock points toward a single event, unfolding in a single span of time, yet leaving behind two consequences that appear almost impossible to place beside one another. One speaks of destruction measured across an entire planet. The other records the beginning of conditions that allowed life to expand in ways the earlier world had never supported. Neither story exists without the other. Both emerged from the same collision. The impactor arrived, carrying material that had spent billions of years beyond Earth. Locked within that rocky body was an immense reserve of phosphorus an element every living cell requires. Phosphorus forms part of deoxyribonucleic acid, the molecule that stores hereditary information. It also forms part of ribonucleic acid, which helps translate that information into the machinery of life. Equally essential is adenosine triphosphate, the molecule cells use to store and transfer energy. Cell membranes also depend upon phosphorus to maintain their structure. When the impactor struck the ocean, that entire reserve entered Earth's environment within moments. The largest known nutrient delivery in the early history of life arrived at exactly the same instant as one of the greatest catastrophes the planet had ever experienced. The collision also transformed the ocean itself. Gigantic waves disturbed waters that had remained separated for immense spans of time. Iron-rich water from the deeper ocean mixed upward into illuminated coastal regions where microbial communities could finally reach it. Those same waters now contained phosphorus delivered directly by the impactor. Two nutrients that had previously been limited by entirely different processes suddenly became available together. Their sources differed, yet both traced back to the same event. One arrived from space. The other emerged because the collision reshaped the sea. Above that transformed ocean, the atmosphere carried dust and vapor that reduced the sunlight reaching the surface. Phototrophic organisms endured a period of profound stress while the sky slowly became clearer. When light eventually returned, the water beneath had already changed. The chemical landscape awaiting those surviving organisms differed from the one that had existed before the impact. Nutrients had accumulated during the interval of disruption, preparing conditions for an extraordinary biological response once photosynthesis resumed more fully. Recovery unfolded within an environment fundamentally altered by the catastrophe itself. This relationship challenges familiar ways of describing natural disasters. Geological evidence does not place destruction in one chapter and renewal in another. The rocks preserve both as products of the same physical process. The impact did not first erase one world before a separate mechanism later constructed another. The devastation and the opportunity emerged together, inseparable consequences of a single planetary collision. Every layer, preserving the aftermath, carries traces of both realities without distinguishing one as more essential than the other. Few discoveries in Earth's earliest history present such an unusual pattern. The S2 record does not ask the evidence to become comforting or symmetrical. It instead preserves a sequence that remains scientifically consistent even when it feels counterintuitive. The same object darkened the sky, disturbed the oceans, redistributed nutrients, and helped shape the chemical conditions that supported an expanding biosphere. The geological record leaves these outcomes side by side, asking only that they be read together exactly as they were written into stone. 3,260,000,000 years ago rests so far behind the present that ordinary measures of history lose their meaning. Earth itself was still young, less than 30% of the way through its known existence of about 4,600,000,000 years. Nearly everything familiar today still belonged to an unimaginably distant future. Oceans already covered much of the planet, continents had begun to emerge, and life persisted in its modest coastal refuge, yet the long unfolding story of Earth had scarcely begun. Another 2,800,000,000 years would pass before the first complex animals appeared. Those future seas would eventually fill with creatures whose ancestors could scarcely have been imagined by the microbial communities living through the S2 impact. An additional span carried the planet toward forests, insects, reptiles, flowering plants, birds, and mammals. Humans would not arrive until roughly 3,250,000,000 years after the collision. Every civilization, every language, every written memory belongs to the final fraction of a timeline that had already stretched across incomprehensible ages before our own story opened. The rocks preserving the S2 event endured through all of it. They already existed before the earliest fish moved through ancient waters. They remained in place before any plant established itself upon dry land. They survived long before the first dinosaur left footprints across riverbanks, and they continued their patient existence after those dinosaurs disappeared. Mountain ranges rose and wore away. Oceans opened and closed. Continents drifted across the globe as plate tectonics, the slow movement of Earth's crustal plates that carries old crust down into the mantle, while new crust forms at mid-ocean ridges, continuously reshaped the surface. Through those immense changes, fragments of this extraordinary record remained preserved. That endurance gives deep time a physical presence. It is easy to imagine billions of years as an abstract number, too large to picture, yet the evidence does not exist only in calculations or computer models. It exists within layers of stone that can be walked across, examined, and sampled. Each thin band records a sequence of events that unfolded long before familiar forms of life appeared. The passing of immense ages has not erased every page. Some remain available to anyone patient enough to learn their language. In the mountains of South Africa, those pages waited within the Barberton rocks. Samples collected only centimeters apart revealed subtle chemical differences that transformed understanding of one of Earth's earliest catastrophes. A geologist from Harvard University, walking those outcrops during the early morning, could hold pieces of that distant world in human hands. The stone itself formed the bridge between present observation and events separated by more than 3 billion years. No imagination was required to invent the evidence, because the evidence already existed beneath each careful step. Perhaps that is the most enduring quality of deep time. It is neither unreachable nor entirely lost. The immense distance separating the modern world from the Paleoarchean has been compressed into tangible layers that fit within a scientist's palm. Those rocks continue to yield new discoveries because they have faithfully carried their record across nearly the entire history of our planet. They remind us that Earth's earliest chapters have never vanished completely. They have remained present all along, waiting within stone for someone to read them. A single living cell carries within it a history far older than memory. Every heartbeat, every leaf unfolding toward sunlight, every bacterium dividing in seawater belongs to the same uninterrupted biological story that has continued since the earliest chapters of Earth. Across billions of years, species have appeared and disappeared, continents have shifted, climates have changed, and oceans have transformed, yet life itself has never broken into separate beginnings. It has remained one continuous lineage, branching again and again while never losing its connection to the organisms that came before. That continuity leads to a remarkable conclusion. Every organism alive today, every bacterium, every fungus, every plant, every animal, and every human being descends through an unbroken chain of reproduction from organisms that survived the S2 impact and the other immense collisions of the Archean world. This is not a poetic image or a symbolic comparison. It follows directly from evolutionary biology. New life has never emerged independently to replace what existed before. Each living cell comes from another living cell, stretching backward through countless generations until the chain reaches those resilient microbial communities that endured Earth's earliest catastrophes. The individual links in that chain have changed beyond recognition. The microbes living along Paleoarchean shorelines shared little outward resemblance with the forests, coral reefs, whales, birds, or people that would appear billions of years later. Their genes accumulated changes across immense spans of time. Populations divided, adapted, and diversified into forms that transformed the planet. Even so, every generation remained connected to the one preceding it. No gap interrupts the sequence. Life alive today inherits its existence through that uninterrupted succession. The same continuity extends beyond hereditary information. The phosphorus delivered by the S2 impactor entered the ocean immediately after the collision. From there, it became available to microbial life, recovering within newly enriched coastal waters. Those atoms passed into living cells, helping build ribonucleic acid, adenosine triphosphate, the molecule cells use to store and transfer energy, and the membranes surrounding every cell. As organisms lived, reproduced, and eventually died, that phosphorus returned to the environment, where it entered new generations through an endless cycle. Across billions of years, the same element continued moving between rocks, water, and living organisms without ever losing its role in sustaining life. That ongoing circulation reaches the present, the phosphorus forming the molecules inside the cells of every person alive today has traveled through innumerable organisms before arriving here. Individual atoms have followed different paths, and no scientist could trace a specific atom directly from the S2 impactor into a modern cell. The broader cycle, however, is firmly established. Material delivered during Earth's distant past became part of the planetary reservoir from which life has continuously drawn ever since. Every living organism participates in that same exchange today. Seen from this perspective, the S2 impact no longer belongs only to the remote Paleoarchean. Its consequences extend through every generation that followed, because none of those generations stood apart from the ones before them. The lineage remained intact. The chemistry remained in motion. The biological story never restarted. It continued, cell after cell, across more than 3 billion years, until it reached the living world that now carries that ancient inheritance without interruption. There comes a point where the evidence asks for careful observation more than confident conclusion. Layer after layer of stone has described impacts, waves, darkness, recovery, and change with remarkable consistency. Taken together, those records begin to suggest something about the nature of life itself. The picture that emerges is difficult to summarize with familiar words. Life does not appear merely fragile, waiting to be broken. Neither does it resemble something impossible to destroy. It occupies a narrower, stranger space between those ideas, where persistence depends on chemistry unfolding under circumstances that no organism could ever foresee. The living world of 3.26 billion years ago possessed none of the features often associated with resilience today. There were no forests spreading across continents, no reefs sheltering thousands of species, no animals capable of movement across landscapes, and no nervous systems able to sense approaching danger. There was no complexity built from billions of interacting organisms. The biosphere consisted almost entirely of microscopic life inhabiting shallow coastal waters where sunlight reached the seafloor. Those organisms could not predict the arrival of a carbonaceous chondrite, a carbon-rich space rock containing organic compounds and water-bearing minerals. They could not migrate away from the impact. They could not prepare for the changes that followed. Even so, they remained present after the catastrophe. Their persistence rested upon metabolism, the countless chemical reactions that allowed each cell to gather energy, repair itself, divide, and continue. When phosphorus entered the ocean from the impactor and iron rose upward through the water carried by the immense waves, surviving microbes encountered an environment unlike the one that had existed before. Cells already capable of using those materials continued their ordinary chemistry under extraordinary conditions. The result was not a return to the earlier state of the ecosystem. Biological activity expanded into new possibilities created by the altered environment itself. Nothing in those rocks suggests intention or design. The microbes did not recognize opportunity. They responded according to the chemistry encoded within their living systems. Natural selection acted upon countless generations that followed, preserving combinations of traits suited to the transformed world. Evolution unfolded without destination, guided only by inheritance and changing conditions. Looking backward across billions of years, the sequence appears coherent, although every individual step depended upon circumstances that could never have been anticipated. This makes the S2 record especially compelling. The geological evidence does not describe life as something that merely withstands catastrophe until normal conditions return. Instead, catastrophe becomes woven directly into biological history. Environmental disruption alters the resources available. Those altered resources influence which organisms flourish. Their descendants inherit the consequences, carrying them into future ecosystems that differ from those that came before. Recovery and transformation become inseparable processes unfolding through ordinary cellular chemistry. Perhaps that is the most enduring thought preserved within these rocks. Life does not answer catastrophe with determination or foresight. It answers through reactions occurring inside living cells, repeated across generations until entirely new biological worlds emerge. The evidence leaves no final definition of what life truly is. It offers something more enduring, a record showing that wherever chemistry remains capable of continuing the chain, evolution keeps writing the next line, even when the story changes in ways no living organism could have imagined. The same shoreline remains, though nothing upon it is quite the same. The water that once rose under impossible force now moves with familiar rhythms again. Across the open sea, the last fine particles drifting through the upper atmosphere continue their gradual descent. Weeks become months. The sky clears one layer at a time, allowing sunlight to return in measured intervals. Day after day, more light reaches the surface than it did before, until the ocean once again reflects a sky that has recovered from its long interruption. The great wave has already spent its energy across distant shores. Heat that spread through the upper waters begins to fade into the wider sea. The violent mixing has ended, leaving currents to resume their ordinary circulation. Nothing announces the transition. There is no dividing line between catastrophe and the world that follows it. The planet continues through its natural cycles, carrying forward every chemical change left behind by the impact. Within the iron-stained shallows, where sunlight now reaches farther into the water, microscopic life resumes the work it has always performed. Phosphorus delivered by the impactor remains dissolved within the recovering environment. Iron lifted from deeper water still circulates through the coastal sea. Together they provide resources that had been scarce before the collision. Cells already adapted to use those materials continue dividing, harvesting energy, and building new biomass. Their metabolism follows pathways shaped by natural selection across countless earlier generations. Yet the environment surrounding them has become richer than it had been during the season before the impact. Growth spreads through the microbial communities with increasing abundance, changing the character of the ecosystem without any intention or awareness. Nothing living recognizes how close the margin had been. The microbes possess no memory of towering waves, no understanding of celestial impacts, and no anticipation of the distant future. Each cell responds only to the chemistry immediately surrounding it. Nutrients enter, energy is transformed, molecules become new cells. Generation follows generation with steady persistence. Evolution continues through ordinary biological processes, never announcing that history has taken a different course. Earth itself offers no reflection upon what has occurred. The oceans continue exchanging dissolved minerals with volcanic rocks. Rain falls into the sea. Rivers, still few across the young world, carry weathered material toward the coast. The crust shifts according to forces far below the surface. Every process belongs to the same living planet that existed before the collision, although its future has been redirected by consequences unfolding one microscopic step at a time. 3.26 billion years have passed since those waters received the first returning sunlight after the impact. Across that immense span of time, continents formed and disappeared. Mountains rose and wore away, and living lineages branched into forms beyond anything those early microbes could have embodied. Yet the chain remained unbroken. Tonight, the same story reaches its latest moment. Between that distant shoreline and the listener resting in darkness stretches an unbroken history written in stone, water, chemistry, and life. The ocean continues doing what oceans have always done, holding living things, carrying nutrients from one generation to the next, and preserving the continuity of a world that never stopped becoming.